In this video, we continue going over looking at colligative properties. In the previous video, just considered that colligative properties are properties which do not depend on the identity of a substance but just on the concentration of solute. And we looked at boiling point elevation as one of the colligative properties. Now we proceed and look at other colligative properties. And the second one we want to consider is going to be freezing point depression. Now, what really happens when you have got a solute, you add it to a solvent. And in this case, our solvent which we are interested in is water. So if we've got water in, let's say, a dish or just something, we know that water gets to freeze at 0 degrees Celsius. So if we get this water and put it in a refrigerator, and it's supposed to be converted into ice at 0 degrees Celsius. But say we add salt, or let's say we add sugar, that is going to be our solute. Now we have added sugar inside the water. What does this do? Well, on the boiling point, we saw that the addition of a solute to a solvent increases the boiling point. Now, when it comes to freezing point, the addition of a solvent is going to reduce the freezing point. So that is what we call freezing point depression. And how do we know that? So here the change in freezing point is calculated by negative Kf multiplied by molarity multiplied by the Van Hoff constant. Now Kf, this is the molar freezing point depression constant. And I'm mentioning molar, not with R at the end, with L. That is because we're interested in molarity and not molarity. And so I is still the Van Hoff constant, as we considered in the previous video. For non-electrolytes such as organic compounds, carbohydrates, they do not dissociate, so the Van Hoff constant is always equal to 1. But for ionic compounds, those which are going to dissociate, when you look at the charges, how many charges do they have? For example, aluminium carbonate. Okay, aluminium carbonate like that. If this dissociates, this is going to give us 2 aluminium positive and also 3 carbonate 2 minus. So looking at the charges, we've got 2 charges here, we've got 3 charges there. So the Van Hoff constant is going to be equal to 5. So that is how we get the value for I, the Van Hoff constant. Now, let's consider when you've been given a certain problem and want to calculate the freezing point depression, or even the point at which the substance is begin to freeze. Okay. So let's say you have got, if you add 5 molar aluminium chloride to water, what will be the new freezing point? Okay, so that is our question. We add 5 molar aluminum chloride to water. We want to determine the new freezing point. But we know that the molar freezing point depression constant for water, Kf, that is for water, this is a constant and that is always equal to 1.86. Alright, and this is given in degrees Celsius per molar. Let's go on. How do we get to calculate this one? And we know already that the change in freezing point is equal to negative molar freezing point depression constant times molarity times the Van 't Hoff constant. And so the change in freezing point is going to be equal to negative the kf, that is 1.86. Well, we are putting negative because we are saying this is depression. It always reduces, so the negative is meaning a reduction. The molarity here, we've been given 5 molar of aluminum chloride. At times the 5 molar wouldn't have been given, they would have given us the mass of aluminum chloride. We know how to find molarity. So molarity is equal to number of moles of solute divided by the mass of solvent. Solvent is the liquid in which you are dissolving, and this should always be in kgs. So perhaps you've been given the volume of the water and they've given you the mass of the solute. Here they've given you the mass. Here they've given you volume. How do you get to calculate the molarity? You know that you find number of moles by mass over molar mass. So the formula becomes mass over molar mass and then divided by. Now if you have the volume, you want the mass of the solvent. They've given you the volume of water. How do you find volume? You know that volume is given by density the mass is given by density multiplied by volume. So that is going to be it. And so this formula becomes mass, this is the mass of solute divided by the molar mass of the same solute multiplied by the density of the solvent and then multiplied by the volume of the solvent. So that is how we are able to calculate now the molarity. And this is going to be in kg, in mole per kg. Well, let's go on and multiply the molarity. We've been given that it is 5 molar. The Van 't Hoff constant, we've been told aluminum chloride. If this disassociates, is going to give us aluminum 3 plus 3 chlorine minus. So the charges, we've got 1 and then 3. So the Van 't Hoff constant for aluminum chloride is 4. So this is going to be multiplied by 4. Well, what value are we going to get? So if we do the multiplication, we're going to get negative 37.2 degrees Celsius. Now, this is the change in freezing point. And how do you calculate change? Change in freezing point is given by the final freezing point minus the initial freezing point. So the change is negative 37.2 degrees Celsius. We don't know the final, but we know that the normal freezing point for water is 0. But if we add aluminum chloride, what is it going to become? Well, 0 minus anything just remains that same thing. Therefore, the freezing point will now be at negative 37.2 degrees Celsius. That is how we get to calculate the freezing point. But note that at times we can be given the change in freezing point. They want us to determine the molar mass. Okay? They want us to determine the molar mass, thereby identifying what compound we have used, and that we are able to do it. So if they've given us this value, we want to determine the molar mass. All we do is, how do we get to calculate that? Now, let me just give the formula. If they've given us the change in freezing point depression, or let me just say the change in freezing point, or they've given us the final freezing point, we are able to do that. We know that change in freezing point is equal to negative kf, but molarity can also be found by this formula which is here. So just go on and substitute that formula, mass of solute divided by, that is molar mass of solute multiplied by the density, if they've given you the density of solvent, multiplied by the volume of solvent, and then you also have the Van 't Hoff constant here multiplied by I. So really, if you want to calculate this, you just substitute in the other values which have been given, and that will be it. Well, now that we've looked at the freezing point depression, let's look at another colligative property. And the third one we want to consider is vapor pressure lowering. Now, what is really this called vapor pressure lowering? Well, if we have got liquid water, let's say we have got water in a vessel, like that, that is our water. Now, vapor pressure is simply the pressure that converts a liquid into a gas. That is what we can basically say as vapor pressure. Really not anything that difficult. So really vapor pressure is simply the tendency of a material to change into a gas. The tendency of a material to change into gas. Now, just like we looked at boiling point is going to be increased when you add a solvent, let me say a solute to a solvent. A solute can be a salt, sugar, or anything that you've added. The boiling point increases. That means it becomes very difficult for you to convert that liquid into a gas. Now, vapor pressure lowering, that also means vapor pressure is the tendency of a material to change into vapor. And so if you add a solute to a solvent, you are going to lower the rate at which, or the tendency of that liquid to change into vapor. So the tendency of it changing is going to be lowered. That is what happens. Just like boiling point increases. So if we increase the boiling point, that means we have to supply a lot of energy for us to change, okay, for us to change this liquid into a gas. That is the same thing with vapor pressure. The tendency of a material to change into gas as you increase, okay, and vapor pressure gets to increase with temperature. How do we get to find the vapor pressure? Okay, how do we get to find the vapor pressure? All right. Now, vapor pressure, if you have like the solution which I'm just from drawing, liquid water itself has got its own vapor pressure. It has got its own tendency. Pure water has got its own tendency of changing into a gas. So it has got its own vapor pressure, and so that we are going to call it as the vapor pressure of the solvent. That is the vapor pressure of the water. But when we get to add a salt or just anything, we are going to change the vapor pressure, because the addition of a solvent, that is a liquid, and a solute, that is something that we have dissolved, this gives us a solution. So together, and what you've added into it, when they come together, they are going to react, and so that is going to form a solution. Really, it might not be a reaction, but they are going to mix, and so they form a solution, and the vapor pressure of a solution gets to lower. Now, how do we get the vapor pressure of a solution? So the vapor pressure of a solution, that is vapor pressure of a solution, it is given by the mole fraction of the solvent multiplied by the vapor pressure of the solvent. That is how we get to do it. So the solution is to get the mole fraction of the solvent multiplied by the vapor pressure of the solvent. But how do we get to calculate the mole fraction? Well, imagine you have got water, and now you mix, maybe you put salt there. So this will form now a salt solution. So to get this which we are calling the mole fraction, this is simply calculated by the number of moles of the solvent itself, because we're talking of the mole fraction of the solvent. So the number of moles of the solvent, in this case we are using water, divided by the number of moles of the solution, and the solution is made up of water and the salt. So that will be the number of moles of water plus the number of moles of the salt, and then we are going to multiply now this by the vapor pressure of the solvent itself, the pure water, when nothing has been mixed. So that is how we get to calculate the vapor pressure lowering, and that we are able to determine very well. It's just simple, just get to substitute. The vapor pressure of the solvent is going to be given If they've given you the mass of the solution, or let me say the mass of the solvent phase, that is the water, and the mass of the salt that you've added, you can simply divide by their molar masses. For example, if they've told us that 15 grams of, I can use sodium chloride, is mixed with, let's say, 20 grams of water, we want to determine now the new vapor pressure of the solution. What we do first, determine the number of moles of the salt, and that is mass over molar mass. The mass of course is 15. The molar mass, that is a 58 for sodium chloride. So let's get to divide 15 divided by 58. That is about 0.2586. These are in moles. And we get to find the number of moles of the water, that is simply mass divided by the molar mass, and the mass is 20. The molar mass of water, that is 18. So 20 over 18, that is about 1.11 moles. So to find the vapor pressure of the solution, this will simply be the number of moles of the solvent, that is of the water, 1.11, divided by the sum of the number of moles of water, which is 1.11, plus the mass of the salt. In this case, the salt is sodium chloride, which is 0.2586, and then multiply by the vapor pressure of the water, which is the solvent in this case, and the water, the vapor pressure is going to be given. So doing this, we are going to be able to calculate the value. So that is how we find that one. Now let's look at the last colligative property. And the last one we want to consider is osmotic pressure. Now, to understand osmotic pressure, we have to talk about osmosis. And we know that osmosis is the movement of water from a region of low concentration to a region of higher concentration. For example, let's say we have got a tube like that, which is open on one end. Okay, so like that. That is the tube which we have. Now, let's say we have got a semi-permeable membrane at this point, which can only allow very small substance to pass through it. And let's say here we have got pure water. Okay, I'm going to put pure water in red, this side. So this is our solvent, that is our water. Now on the other portion, we are going to have a solution. A solution contains a solvent mixed with some other things. For example, it can be a salt solution. So this is a solution. Well, so what is going to be happening if you have got water this side, which is a solvent, and then you've got a solution this side? So the solution has got higher concentration of particles. Water is pure, so the concentration of particles is very little. That means we have got more of the water than anything else. And water is a very small molecule, and so what is going to be happening is the water is going to be penetrating, going into the other solution. So water tends to move. It tends to move from this to that. It gets to move like that. Well, the flow doesn't just happen like that, because even in the solution we have got some little bit of solvent. We also have a little water in this solution. So even here some water is going to be moving from the solution into the solvent. But because we have got a lot of water here, we have got a little there, the net flow is going to be in this direction than in both directions. Now, what happens in that? So the reason as to why water is moving from this region to the other region is we want to reach a point where the concentration in both solutions is the same. So what we are going to form be something like, let me put another one. Okay, like that. So because water is moving from this region going into the other region, water is going this region is going to be increasing in volume and the other one is going to be reducing. So we are going to have more this side, and we still have our semi-permeable membrane here, and in the other side this is going to be the level will be much lowered, because at this first point they were all on the same level, but now we can see they are at different levels. So at this point now we have reached a point of equilibrium. The solution and the solvent is at equilibrium. That means the concentrations in both are now the same. Now just this difference between here and here, this is what we refer to as the osmotic pressure. Just this difference. Why all this change to reach equilibrium? So such is referred to as the osmotic pressure. I can give that to be the symbol. It is more like pi, but okay, let me put like that. So that is the osmotic pressure. Now, osmotic pressure is simply the minimum pressure that you have to apply to the solution side for you to stop fluid movement. What are we talking about then? Remember, solution fluid movement is moving in this direction. Now, if you apply pressure here, instead of water, the solvent which is here moving in this direction, what is going to be happening is the pressure which you are applying is going to be forcing the little molecules of water which you have in this solution to be forced to go in that direction until a point of equilibrium is reached. So just a very minimum pressure that you have to apply to the solution side to force particles, or to force these molecules to move, the water molecules to move, or to force molecules to move to the other solution. That is what we call osmotic pressure. And we can simply say osmotic pressure is the minimum pressure that is applied to the solution side to stop osmosis, so that the movement of water doesn't happen. We need to apply certain pressure here to the side which is more concentrated. Minimum pressure applied to stop osmosis is called osmotic pressure. So that is it. But how do we get to calculate the osmotic pressure? Well, just like other colligative properties. Now, osmotic pressure, which will give like pi, that would be the symbol. It is given by molarity multiplied by the universal gas constant multiplied by the temperature and then multiplied by the Van Hoff constant. And it is the only colligative property where we use molarity instead of molality. So the others, boiling point, elevation, freezing point, depression, vapor pressure lowering, we've been using molality. But for this one, what we are using here is the molarity. So the difference is there is R here, and for this one there is L, and that changes everything. So that is how we get to calculate the vapor pressure. I mean the osmotic pressure, not vapor pressure. Well, in this video I end here. See you in the next video where we'll get to go over many more practice questions on colligative properties and also other things on phase equilibrium.